Okay, it is now time to dig into the Floyd-Warshall algorithm. So we've got an animation problem again. What is the optimal substructure for the all-pair shortest path problem? So here's our key concept. We're going to label all of our vertices from 1 to n, giving them any arbitrary order. It doesn't matter. And we're going to introduce some new notation here, call it v superscript k. And that's going to say take just the vertices 1 through k. So our optimal substructure lemma for the Floyd-Warshall algorithm is first we're going to assume that the graph does not contain negative edges. And then we're next going to fix a source vertex I and a destination vertex j and a value for k. And we're going to say let p be the shortest I to j path only using internal nodes from vk. Okay, so there's a lot going on there. Let's look at this in terms of a diagram. So this is just copied over from the previous slide. But let me give you some specific values for I, j, and k. All right, so let's say I is node 17, j is node 10. So that gives us just sort of these highlighted vertices as the ones that matter. There are probably more vertices out here. Let's just say that they don't connect into what we're talking about here. So my first question is, what is the value of the shortest path found by the Floyd-Warshall algorithm? Well, I'm being a little annoying here. I've not actually given you enough information for this. I gave you I and I gave you j, but I didn't give you k. So how about if I give you k is equal to 5? That means we can only look at the vertices 1 through 5 as nodes along the path. So with the vertices 1 through 5, we've got 1, 2, 3, maybe 4 somewhere off the screen, and here's 5. What is the shortest path from 17 to 10 using only internal nodes from vk? So I can only use these 4 nodes, and then 4, which apparently is not connected in here anywhere. I can only use those nodes on the path. Well, given that extra information, the shortest path is this one. And the length of that shortest path is, let's see, 5 plus 2 is 7, minus 4 is 3. So even though we have a shorter path here, we can't find that path until k is equal to 7. Okay, so let's talk about our optimal substructure lemma again. Suppose G has no negative cycles, and we're going to say let B be the shortest path from I to J, where all internal nodes come from BK. Then we have 2 cases that we want to consider. We want to say, what if K is not internal to P? Well, in that case, we can say that P is also, so that shortest path is also a shortest path from I to J, with all internal nodes from V of k minus 1. So going back to this previous one, it's like saying that this shortest path that we've determined here is also the shortest path for k is equal to 4. It's also the shortest path for k is equal to 3. So that's case 1, when we don't use the maximum k-valued vertex. Case 2 is when the vertex k is internal to P, meaning it shows up on the path. In that case, we care about the shortest path, P1, from I to k. And we can only use nodes from vk minus 1 for that part of the path. And we also care about P2, which is the shortest path from k to j, also using nodes from vk minus 1. Okay, so what does that look like in picture form? Well, if I have a vertex I and a vertex j, I can have sort of any number of vertices on that path. And let's say that one of the vertices on that path happens to be k. Well, P1 is this part of the path, and P2 is this part of the path. All right, so let me show you that in another diagram. And by the way, I skipped past it here, but what is k effectively doing? It's splitting the path P, the green P here, into 2 optimal subproblems, the path P1 and the other path P2. So case 1 is when all of the vertices along the path have a value less than k. All the internal nodes have a value less than k, meaning k is just not on the path. Case 2 is when k is on the path. And the total path is the same in both cases, Maybe not the same vertices in both cases if we're talking about two separate scenarios, but it's the total path from I to j in both cases. For case 2, when we have k, we've got two components to that path. The path from I to k and the path from k to j. And what we're saying is that this path is optimal and this path is optimal, and we don't have to have k on those paths because k is that vertex. So they're both optimal. The subpaths p1 and p2 are optimal with respect to v of k minus 1. Alright, so what are the base cases for the Floyd-Warshall algorithm? Well, in this case, we're going to be filling in a three-dimensional array because in the end, we want to have the shortest path to all pairs of ij. And as we said, we're limiting ourselves to k vertices at any given iteration. So that's why it's a three-dimensional array. Which index, ij or k, should be representing our base case? Another way to say that is, what do I fill in first in the table? Well, I can always fill in the case when I don't allow any internal nodes. So that's sort of the easiest thing to do, the easiest rows or columns, or since this is a three-dimensional table now, you can think of it as like the base layer of the table. What is the value of that base case? Well, we have three different scenarios. Our first scenario is when I is equal to j, and in that case, we can just say that the length of the path is 0. Another case is when there's a direct edge from I to j. Well, there are no internal nodes on a direct edge, so the length of that path is just whatever the cost of the ij edge is. And then finally, there is no edge directly connecting I to j. So in that case, it's an infinite path length. All right, well, now let's take a look at the code for this. Floyd-Warshall takes a graph, and we don't have to worry about passing in a start vertex because it's going to calculate the length of the path from every vertex to every other vertex. It doesn't matter where we start. We're going to have a three-dimensional array here, so it's n by n minus 1. So the first dimension would be like I, second dimension would be j, and this is going to be k, which we're allowing to be 0, as well as the maximum number of edges on a path, which is n. N minus 1 actually, but we always go one extra iteration to check for negative cycles. Same as we did for Bellman-Ford. Okay, well the next case is to fill in our base case, so we're going to loop over all from vertices and look at all two vertices, and if it's the same vertex, we just pass in a length of 0. If there's a direct edge going from v from to v2, we just pluck out that edge weight. Otherwise, the length of that path is infinity. So there are our three cases we enumerated on the previous slide, and here's what it looks like in terms of code. Okay, and then we have to build the table next. So we'll continue that on the next slide. On the next slide, just so everything fits, I'm going to collapse this all down, and we'll start building the table from here. All right, well, as you might expect in a dynamic programming algorithm, we're going to do this time we're going to do it in a bottom-up approach, and it's just a bunch of nested loops. And since we have a three-dimensional table, we have three looping indices, and they all go from 1 up to n. Okay, so our first case is when we don't include the vertex k on the path, in which case the path length we care about is, well, how did we get to the from, or how do we get to the to vertex from the from vertex, not using the vertex k? That's the first case we want to compare. The second case we want to compare is, well, what happens if we do use the vertex k? We're going to go from b from to k, so you can think of b from as I on the previous slides, and v2 as j on the previous slides. I like to make my pseudocode a little bit nicer naming as opposed to just sort of the mathematical notation. So we have a v from vertex somewhere, and we have a v2 vertex somewhere. And one possibility is we have some path that we follow that does not have k. Another path that's possible is that we're going to include the k vertex, in which case we have these two parts of the paths. So what we want to do is figure out the minimum. Is the path minimized by not using k, or is it by using k and these two subpaths that are also both optimal. So we know that this path here is optimal and this path here is optimal, and we're adding them together. All right, so that's the Floyd-Warshall algorithm. What's the running time of this algorithm? Well, we do in fact just loop over n 3 times, so this is big O of n cubed. How about correctness? Well, we talked about the substructure lemma a little bit, and I'll leave that up as an exercise to you to convince yourself that this part here is true, that these two subpaths are true. And you can look through that using a variety of different ways. I think a proof by induction is particularly useful there. All right, so where are the final answers? So where in the table are the final answers? How does it handle negative cycles? And as we'll see, well, I guess we won't see. I decided to cut that out of the slides here. Reconstruction is actually very similar to previous ones. You start at the end of the end solution and work your way back. Okay, well, let's answer these two questions then. Where are the final answers? Well, let's say that I want to find the shortest path from vertex 10 to vertex 17. Where would that be found? It's going to be in my path links array, going from 10 to 17, using all n vertices. Oh, sorry, a maximum number of n edges. All right, next question is how does it handle negative cycles? Well, how do we check if there are negative cycles? So I'm going to put a pause on the video here so you have a chance to think about it. Where in the table would you examine and look for negative cycles? Well, this should be very intuitive. There's a few different ways to do it, but the easiest way to do it is to look in path links and just look for every vertex. So look inside here. And for every vertex, look at the value when you have the same v from as it is v2. So if those are both v, and then this is n, that's essentially saying what's the length of the path from a vertex to itself using the most number of edges you can use. And if that happens to be a negative value, then we have negative cycles, meaning there's a path back to itself that reduces the path further than 0. Okay, so that's the Floyd-Warshall algorithm.